about some joint work with my advisor, Andrew Hirsch, and another UB colleague, Matt Nepoli. Specifically, we're bringing choreographic programming to high-performance computing through the Message Passing Interface, or MPI. Now, I expect you know some about choreographic programming, not about MPI. That's exactly where we're going to start. Importantly, for the next 20 minutes, this is not the Mont Planck Institute. This is the Message Passing Interface. OK. So what is MPI? MPI is the default standard for high-performance computing, or HPC. I say it's the default because it's being used everywhere in medical, aerospace, and energy research. It does things like simulate the possible spread of COVID so we can help better combat it. It's doing things like launching humans around the moon with the Artemis II mission. It's doing things like setting the next generation of nuclear safety standards at the Argonne National Lab. So everybody's using it, or something derived from it, but everybody's using MPI. And importantly, MPI is not a language, it's a library specification which is then implemented in different languages. Typically things like C, C++, and Fortran, but there are also implementations in OCaml, which we'll see later. But for the most part, we're thinking C and Fortran on clusters and supercomputers. Okay, we have to learn a little bit more about the specifics of MPI to sort of talk about what makes it really interesting. So to start with, we're going to talk about groups. So we're working with clusters. We have lots of processes or nodes, which are going to be using interchangeably. Now let's consider a system of 8 nodes. Now, if this is our entire system, this will form a group, the global group, and groups are just logical collections of processes. So in our group, every process has a rank or its name. Importantly, these are sequential integers starting at 0, going to n-1 for a group size of n. All right. And importantly, you only have a rank, you only have a name in the context of a group. So you're only 0 in this group. You're only 1 in this group. Now, sometimes I don't want to talk with the entire group, like I am right now. Sometimes we want to split off, like when we go to lunch. And for that, we can make another group. So we can now organize what were global 4, 5, 6, and 7 into a new group, where they're now 0, 1, 2, and 3. And we can do this pretty much as many times as we want. We can build groups out of any of our processes. This is really nice. The other important thing to know about groups is that 0 is the root of a group, and sometimes it has a special job. Alrighty. Groups are important because they show up everywhere. All communication happens within the context of a group. Remember, you're only 0 in a group. So when we want to do point-to-point communication, 2 nodes sending messages to one another, we have to talk about it within a group. So if I ask 0 to send to 1 in the black group, our global group, and I peel back the curtain, that's really blue nodes 0 and 1, because it's the global group. OK. However, I can ask the same thing of our red group. In the red group, I want 0 to send to 1. And now when I pull back my curtain, I'm instead talking about 4 and 5. OK. But the MPI developer said, you probably don't want to organize 1,000 nodes with point-to-point communication. Let's give you something a little more powerful that you can use. And we have a couple collective communication operations we need to use. The first is broadcast. So in a broadcast, your root, this is where they have special jobs, is going to send the same information to everybody in the group, including itself. So 0 takes its piece of information, and everybody ends up with a copy. All right. That's great, but sometimes we want to do distributed computation, where everybody gets a piece of the puzzle to work on. And for that, we're going to need scatter. So scatter is going to split an array into equal-sized pieces and send a piece to everybody in the group. The piece of the array you get corresponds to your rank in the group. So 0 has its array, it splits it up, and everybody gets their piece of the problem to work on. Alrighty. Once we do our computation on those pieces, we want to collect it back. And for that, we're going to need gather. So gather is going to take a piece from everybody, send everything to the root, and the root is going to organize it back into one array. Again, the order of this array is determined by your rank in the group. OK. That should be more or less all the information we need for MPI. If anything else comes up, don't worry, I'll let you know. OK. So now we have 2 questions to answer. One, is deadlock freedom of MPI programs important? This is choreographic programming, so when we're talking verification, we really care about deadlock freedom. And the answer is yes. MPI programs are answering important questions, and they're really expensive to run. Time on clusters isn't free, and it's not cheap. So you want to make sure your program doesn't get stuck and you have to run it again. All right. Our next question is, well, why choreographic programming? Why is this the vessel to talk about deadlock freedom for MPI? And the answer there is, well, MPI programmers are already doing pseudo-choreographic programming. What's that mean? Well, let's look at what it means to write an MPI program. In MPI, you write one global program, and then this global program is run at every node in your cluster. So everybody runs a copy of your program. This means if you want to specify behavior for a specific node, say 0 of the global group, you're going to be using big if then else statements. This is very similar to choreographic programming, where again, we start with a global program, but instead of a copy, we project. So we project into individual programs for your different nodes in the system. Okay. So MPI programmers and choreographic programmers are all starting at the same global program idea. It's even more similar when we look at specific programs. Before I show you any actual MPI code, it's verbose. I apologize. And also remember, we're typically working in C and Fortran, so everything is numbers. But we'll get through it, I promise. OK, the first thing to notice is this big if then else branch. This is what I'm talking about. If you're 0, run this code. If you are 1, then run this code. What are you doing if you're 0? Well, you are sending to process 1 of MPI COM world. MPI COM world is just your group. It's the global group that we were talking about. All right, and importantly, the other half of that, if you are 1, well, you better be receiving from 0 of the global group. OK, so there's a lot up here, but we can make sense of it. All right. On the left-hand side, we're going to see a little bit of the choreographic and network language. We'll talk more about them later. But to start with, as choreographic programmers, we see these separate sends and receives, and we want to piece them together. And we can do just that. Before we do that, for brevity, I'm going to call MPI COM world G. So that's going to show up. But we can piece our separate sends and receives together, and we end up with the same information. So within this group, 0 is sending the message data to 1. Alrighty. And then when we project it out, we see this separate send and receive that we saw over in MPI. So MPI programmers are almost thinking about projection on their own, and I don't want to do projection on my own. I want the computer to do it. All right. The story is even more similar with collective communication. In MPI, when you want to write a broadcast, every process in the group has to write this expression, where you're broadcasting data to this global group. Importantly, this is different, or interpreted differently, if you are the root or if you are not the root. If you're the root that says, hey, I better send to everybody, and if you're not the root that says, hey, this is going to be a receive from the root. Not literally, but this is how it behaves. Okay. And this is very easy to translate into a choreographic world, where again, we're just broadcasting data to our global group. So hopefully you're convinced. And that leads us to what we're doing. Well, we are writing Chor MPI. It's a choreographic HPC language based on MPI to ensure deadlock freedom. 2 caveats here. Based on MPI. Why that? Well, we're working with a functional subset of the MPI standard. The MPI standard is 1,200 pages long. We cannot capture all of it, but we have a core message passing part of it. We feel confident of this because we're working with Matt Nepoli, the other collaborator here. He is a core developer of PET-C, a well-known HPC library that supports things like MPI. So he has been instrumental in helping us decide what parts of MPI to focus on and what is the MPI standard actually telling us to do, because the MPI standard is all natural language. OK. So now we get to talk about languages, the actual languages for this project. We're going to start with a network language, so Lambda MPI. As its name suggests, it's Lambda calculus. In fact, it's a concurrent Lambda calculus. Some of the interesting things about Lambda MPI are the same things that make MPI interesting: point-to-point communication, collective communication, and extensive group calculus. So again, we have our sends and receives we saw before. We have broadcast, scatter, and gather as primitives. And then we have just a handful of our group operations. I would love to talk more about the groups and the group calculus we've come up with, but I just don't have time today. So if you want to hear more about that, find me another time. It's really interesting. All right. This is cool, but it's more than just what we're going to project to. Lambda MPI also gives us a nice model of MPI. That 1,200-page MPI standard written in natural language is hard to work with. This gives us something to do math with, which is much nicer. And of course, we are also working to mechanize proofs about this language in Rock. This is a work in progress. This is also how I'm learning Rock. So this is going fairly well. Alrighty. Now, finally, the choreographic language. So Chor MPI, it is our work in progress choreographic language. And to start with, let's just see how we can go from the network language to our choreographic language. So again, these mismatched sends and receives, put them together. All of our collective communications look very similar. We are broadcasting, scattering, and gathering, each their own type of communication. All right. But we have a problem. What does it mean to scatter to something? Well, we know what it means, but how do we actually talk about everybody getting a piece of that information? And importantly, what do we do with that information once we have it? And for that, we need to introduce 2 new things. the faceted value, and the SIMD block. So we're going to start with the faceted value. This is a term we are borrowing from the information control community, or information control flow community. So a faceted value is just how we talk about what piece of the array everybody's going to get. So all of these different expressions are what each individual process in group G is going to get, and they all better have type T. I like examples. We're going to start with a 4-process group. The only thing you really need to know about this group is it has 4 processes, so all of our faceted values better have 4 expressions. All right, so the first one, we can give everybody an array of natural numbers. And the second one, we can just give everybody a natural number. So these faceted values do look a lot like arrays. We have a pretty good idea of what we want to be sending. All right, but importantly, if you are the root of this group G, our first faceted value to you just looks like the array 0, 1. So that's all you really need to know. And importantly, again, this just looks like 17, which is a natural number. So from the view of 6, your big faceted array is really just what it needs to know. OK, so that's how we talk about getting the information to different processes. What do we do once we have it? For that, we need a SIMD block, which really cares about 3 pieces of information: a group, a faceted value, and then an expression E. So this expression E is going to run at each of these processes P in our group G. And each of these individual processes is going to have access to X, which is its piece of the faceted value, its piece of what you probably scattered. OK. Importantly, the SIMD block results in another faceted value. OK. Again, I'm a big example person. Let's see these in action. So this is the roll call example. We're going to take an array of zeros. Everybody in the group is going to get a 0. You are going to add your rank in the group to it, and then we are going to collect all of this back at the root. OK. First thing we need is a group, so we'll start there. Back to my favorite group. Importantly, we care that it has 4 processes. All right. Our first actual communication we want to do is scatter. So we are going to scatter. So this is our scatter expression. Importantly, we are scattering this array of zeros, which is located at the root of G, which is always going to be rank 0. Everybody's going to get 1 0 from this scatter. And again, just G again, because we need to talk about what group we're in. And we're going to call this faceted value, because we're going to use it later. We're going to use it right now in our SIMD block. So once we do our scatter, we have our SIMD block. So this says, well, for everybody in our group G, you're going to take your piece of the faceted value. You're going to add your rank to whatever you get. This a.get is an array. We have to scatter and gather in arrays. It's a little onerous, but remember, we're working in C and Fortran, and over there it's buffers. So it could be worse. So we get arrays, they get buffers. All right. So that's just getting the first thing from your array X, which in this case is always just going to be 0. All right. And that's what these square brackets on the outside of it are for. We have to package this back up into an array. All right. So we've scattered our value. We've done our computation. Last thing to do is just gather. And that's all we are going to do. Remember, gather is going to take a faceted value, which is what SIMD is going to result in. Everybody is going to send one thing to the group. And overall, this will give us our roll call example. This gives us a very common pattern that HPC people are looking for. OK. That's a little bit about the language, mostly just some of the communications. Again, it's a work in progress. But I do want to talk about some things we're excited to explore as we continue on with this. So the first is multiply located in SIMD values. So what are multiply located values? Well, that's what we end up with when we broadcast. So in a broadcast, everybody gets the same value. We know what everybody in the group has. I'm not going to talk too much about this because Mako's going to tell us a lot more about multiply located values, I think, later, more or less. I'm going to leave it to the pros. But again, this is not our idea. This has been seen before in languages like he lambda small and lambda quick change. The other exciting piece of this puzzle is SIMD data, so single instruction multi-data. This is what we're working with scatters and gathers. We just saw it in our example. This is why we added things like the faceted value. As far as we know, the only other work to tackle these is Symphony, a language for secure multi-party computation that, when trying to describe some of the more complex computations, ended up pretty much back at choreographies, which is really exciting. So, alrighty. Next up of things we're excited about is endpoint projection. We're hoping to explore 2 types of endpoint projection. The first is exactly what you're thinking of. I take my global program, and I project it into individual programs, like we always do. And that's great. But we also want to explore the possibility of taking our global program, projecting it to one Lambda MPI program, and then having everybody run a copy of that program. The idea here is we still get all of the nice choreographic reasoning with our global program, but it's much more similar to how MPI operates, where everybody's running the same program. There's also hope this could help with scalability. So if everybody just gets the one program, life is easier. Okay. The last thing we're excited about today before we wrap up is we're working on a compiler project with 2 undergrad interns this summer. So they're writing a compiler to take Chor MPI, project it into Lambda MPI, and then finally compile to OCaml with MPI bindings. This is where OCaml shows up. I know what you're saying. Keith, I'm probably not going to be rewriting my MPI in OCaml. Some folks are, and that's great, but most people are not. Again, we're typically in C or Fortran. Our goal is to show that adding Chor MPI, projecting to Lambda MPI, compiling to another language is not adding a bunch of overhead, and we can actually replace OCaml with things like C or Fortran at some point. Okay. So, to sum it up, we have unverified MPI code answering really important problems, literally doing rocket science. But they're already sort of doing choreographic programming. So with a few extra steps, Chor MPI, we can ensure deadlock freedom without really interrupting their workflow too much. And we're really excited about this. We'd love to talk to you about this if this is something you've thought about, if you have ideas, if you have feedback, anything. I would love to talk to you guys about this. And with that, that's the end of my talk. I would love to take any questions.
Hi, thanks for the talk, and what a fabulous motivation for choreographic programming. Could you say maybe just a little bit about those operators that you teased about?
Yes, absolutely.
Yeah, and particularly, is the number of your participants fixed? It looked like you had a union operator.
Yes, so we'll talk a little bit about groups, and I do actually have slides because I was hoping people would ask.
You baited me well.
I did. So things to know about groups. In our model, at least, we have three classes of defined groups, or sort of predefined groups. We have that global group we were talking about, the empty group, and then singleton groups, so groups with just one process. And then we can use our constructors to build all the other groups you want. Importantly, what makes our group calculus interesting is it's a little different from MPI's group calculus. MPI uses union, difference, and intersection, which work more or less how you think they do with sets, but with some extra ordering, because groups have an ordering component to them. We have union, just as they do, but we also have split and shuffle, which I have a couple quick examples if you're an example person. So splitting says, hey, I want to take my group, split it by some function, and this is going to end up with an array of groups we get to talk about. And then shuffle is just permutations of the ordering of that group. And these let us express all of the group constructors in MPI, which there's more than just the 3 I showed, but with the same, just with our 3 constructors. We are working with a fixed number of processes, but you can union groups. So we're not creating more processes, we're just unioning the groups we already have. Okay. Hope that's a nice little overview. Yes, or who has the mic? You have the mic, sorry.
So groups in the sort of Lambda MPI or Choral MPI, choreographic MPI seem to be a combination of communicators and groups from MPI, right? Because groups in MPI are unordered, right? Whereas communicators are ordered. So is there a sense of ordering in your version of groups? Or?
There is. This is another important caveat. In MPI, all communication happens within communicators, one type of which is groups. Groups are the only one we are supporting. When you really get down into it, our groups are sort of a bit of emerging between communicator and MPI in many ways, but there is ordering, absolutely. Okay.
So regarding the syntax of the SIMD instruction, you had that inner body expression E. Can that be a whole program, or is that limited to a sub-expression language?
I don't know. It's a
local program.
Yes, it's a local program.
I don't know that we have any restrictions on it other than, you can't communicate, it's local.
Yes, so probably not communication. Something I took out of this talk, but as I was writing it, the last part of this talk I actually wrote was the Chor MPI example stuff, because that is the newest stuff we're working on. I think we started thinking about the SIMD block stuff, 2 weeks ago. So very, very much work in progress. I'd love to talk more about it. Yeah.
Let's thank the speaker again.